Thank you, John. When I moved to Juneau, Alaska on my birthday in 1971, this was the Mendenhall Glacier. That's me. This is the glacier a few years ago. Climate change has caused 2 reproductive seasons for the spruce bark beetle that's wiping out the forests. The ice goes out earlier in the springtime, exposing the coastline of Alaska to the winter storms, and we're losing probably 10 coastal villages. So this has had a profound effect upon me, a guy who's lived in Juneau, Alaska the last 43 years. And I have concluded, therefore, that our responsibility as human beings and engineers and energy professionals and scientists and business people is nothing less than converting the world's largest industry, energy, from about 85% fossil fuel to over at least 85% renewable source energy, literally running the world on renewables as fast as we can, prudently and profitably. There may be some nuclear. It's very hard to predict that now because these problems have become emergencies. And therefore, we need to move from spending our capital, eventually you'll go broke, what does that mean for our civilization, to running on income. And the only income we have on this planet is solar energy from the sun. This is humanity's total annual energy use, and this is the annual energy input we get from the sun. And therefore, I often title my presentations at scientific conferences, American Society of Mechanical Engineers, as Running the World on Renewables, Alternatives to Electricity. I ask, can we do this? Can we run the world on renewables entirely with electricity, transmission, storage, and integration? And if not, and at this time, we should at least be seriously considering alternatives, moving that energy around and storing it very inexpensively as hydrogen and ammonia fuels. The trouble with renewables, of course, is that they're dispersed. They're all over the countryside. There's a very high gathering cost, and then they're remote, the richest resources, so we have the transmission cost. And they're time varying in their output, intermittent, some have said. So we have the firming storage problem. In the future, we're going to use both distributed, that's the PV on your garage roof and mine, and centralized large solar and wind plants for running the world on renewables. Therefore, we need to think beyond smart grid, which is now being presented to us as the next big thing in the electricity world, some sort of a panacea, but it's primarily a demand-side management tool. It provides no new physical transmission or storage infrastructure for us, and therefore we have to think beyond the electricity systems into complete energy systems, moving air and water molecules and photons to energy services delivered. Nobody wants to buy a kilowatt hour or a liter of diesel fuel. We want the energy services that they provide to provide all of humanity's energy from renewables. And therefore, we need to think beyond transmission as wires. After all, if your only tool is a hammer, the world looks like nails. If your only product is electricity, wind and solar, the world looks like wires. We need to think beyond that. Because low-cost storage is available to us as hydrogen and ammonia, these large anhydrous ammonia tanks that we have around the Corn Belt can store energy at 10 cents a kilowatt hour capital cost. And we can store it as hydrogen in solution mine salt caverns for about 20 cents. So we need to think in the concept, in the context of complete renewable energy systems, and I just happen to have one with me. Perpetual motion. This has been running on our artificial sun over here. This is a hydrogen system, not an ammonia system, but we must wonder, is the abundant and low-cost renewable energy of the future going to be available to us primarily as electricity or perhaps as hydrogen? Because there are many ways of producing hydrogen from renewable sources as well. Now you can see the sun has gone down. We no longer have energy input to the PV panel, and yet the system is running. So clearly, we've demonstrated perpetual motion at this time, or perhaps there's hydrogen storage in the system. So we'll let you place your bets on how long this will run. The point is, we have to think of complete renewable energy systems. And therefore, I'm going to present to you a landscape assessment of what renewable source ammonia looks like now. Talk about a project that our small company tried to do in the state of Alaska. Talk about complete renewable energy systems as we have so far. A conference I attended in July of this year representing the Ammonia Fuel Association on artificial photosynthesis in the UK. And then a study that Ag Ventures Alliance, right here in Iowa, hired our small company to do to investigate a wind to ammonia prospect. It's very windy in Iowa. Is this the good place to get started making ammonia fuel? And from this project, our technical engineering and systems integration company, Wind to Green, took a synthesis technology survey, their own landscape survey, on how to make ammonia from hydrogen and electricity. And then, as a demonstration project, why don't we get our hands on a couple of ICE gensets and have Eddie Sturman or Ted Hollinger convert those to run on 100% ammonia and deploy them in some visible place, work on the demand side of the ammonia equation as well as the supply side. In Alaska, we have more renewable source energy than any place else on Earth. We have more coastline than all the rest of the US put together. It's very windy out here in the Aleutians, and there's the Asia market not too far away. We also have over 150 energy islands in Alaska. These small communities, they have no connection to the outside world, no transmission system, no road system. They're living on imported fossil fuel for heating as well as for electricity generation. It's typically at $6 to $12 a gallon landed cost. And if we could harvest Alaska's vast renewable resources and convert it somehow from renewable source electricity or hydrogen into ammonia, then we could participate in the global trade. In my experience and that of others in Alaska, we can't deploy in an Alaska village, a small community of a few hundred or 1,000 people, a very complex system that electrolysis Haber-Bosch would be. This is the implementation by our friends at Proton Ventures in the Netherlands. May be wonderfully appropriate in some places, but probably not in an Alaska village. And therefore, our company proposed to the Alaska Energy Authority several years ago, in response to the funding opportunity they had in what they called the Emerging Energy Technology Fund, that we build a demonstration facility, a small pilot plant in a Connex container, so it would be transportable around Alaska, and it would bring in renewable source energy. We've got a big switch here. Either we switch it up here and convert it into renewable source ammonia and store it in a steel storage tank, or we flip the switch the other way and we run the ammonia from the storage tank through the ICE genset and put it back into the local renewable energy grid, demonstrating that this could be done economically, technically, feasibly at the village scale. Now this would have only been a few kilowatts input. It would just been a pilot plant to demonstration, concept to demonstration. It was $1 million project. This is $750K our company was designated to receive from this Emerging Energy Technology Fund program. The technology supplier would have to put in $100K in the proprietary components by which the ammonia would be synthesized, and then our system integrator designer would put in $100K of IP in the reactor design. We would put in some management, and it came to be a $1 million project. Unfortunately, the technology was simply not available, and we had sold this project to the selection committee by saying, we understand you want TRL4, technology readiness level. You said that. We think the technology we're proposing is at TRL 2 or 3. If you'll select our project, we will agree not to begin the project, not to sign the grant agreement until we've proven that the basic technology works. And since we didn't, we couldn't get to milestone 1, so we gave the money back essentially on December 11th of last year. But Wind to Green, our system integrator, said, let's do a technology survey of all that's available and other ways. There are many ways, as we've already heard today, of synthesizing ammonia other than the Haber-Bosch method. And darn if every report they came up with didn't conclude with, we need better catalysts, as if there's some sort of needle in the haystack out there that can be found if we only had a more powerful magnet. So there are many new methods and pathways to ammonia synthesis, although all of them seem to be stuck at the TRL, technology readiness level 1 to 3. And therefore, the lowest risk at this time is electrolysis plus Haber-Bosch, which we abbreviate EHB. It's going to be a very long haul in money and time to bring some of these other technologies to the point that they're of high technology readiness level, ready for commercialization. Many of these are going to result in high-cost ammonia at the plant gate. With what will it compete? Will it compete with brown ammonia made from natural gas, long-term contract, $1 or $2 per million BTU stranded gas in Australia? So if it can't compete, what's the point? What's the market? So we have to have markets. And we don't know whether the sources for ammonia synthesis are going to be primarily electricity or primarily hydrogen. If we have hydrogen, great, we can go directly into Haber-Bosch or some other synthesis method. If it's electricity, we're probably going to have an electrolyzer in the system. And here are the obvious markets. We've talked about many of these, and all of these combined would point us on the way to running the world on renewables. There are many carriers and storage strategies for renewable source energy. Obviously, electricity, gaseous hydrogen in pipelines, where the pipelines themselves are storage because you can pack the pipeline pressure. Ammonia, and the Japanese, as we've already heard, have a very interesting concept of moving hydrogen from stranded locations, carbon-free, to Japan as a cycle on commodity tankers on the sea, starting with toluene, hydrating it at the renewable source to methylcyclohexane, H14, returning it, dehydrogenating it on the ground in Japan, putting it back in the tanker and moving it around. So mole for mole, liter for liter, you're bringing hydrogen to the home islands. And artificial photosynthesis, the first step in photosynthesis is water splitting. You're making hydrogen and oxygen. So is that going to be some way a source and a carrier and a strategy for moving renewable source energy around? The organizer of this conference, Tom Faunce from Australia, invited John and Norm to send somebody representing the Ammonia Fuel Society to this meeting of the Royal Society. You might remember that's Isaac Newton's group at Chicheley Hall in the UK. This was our venue. It was tough to put up with, but that's where we were. And their title was a Global Artificial Photosynthesis Project, trying to avoid the IP fights that have emerged and have stalled progress on so many other technologies as the lawyers and the patent trolls go after each other. And so the title of my presentation was, what shall we do with the photohydrogen that you would make, you artificial photosynthesis people, as the first stage in your process? Do you want to take CO2 out of the atmosphere and make hydrocarbon fuels? If so, they can only be used in Carnot engines with relatively low efficiency. Or shall we sell the hydrogen directly? Or shall we make it into ammonia so it's more economically transported? This is the obvious way that you would make ammonia. Wind or other renewable source generators, make hydrogen, air separation unit, transport it by pipeline to distant markets. The electrolyzers have been available for a long time, and as we heard, they're becoming available again in sizes and configurations that would be convenient for this purpose. Electricity and water come into the electrolyzer, nitrogen from the air separation unit, Haber-Bosch reactor, and out comes the NH3. If we could combine these two in some sort of technology beyond Haber-Bosch, we've coined the term BHB. Everybody has to have an abbreviation, beyond Haber-Bosch. Whatever this technology is, now it becomes a lot simpler. This is the term that John's group uses, solid-state ammonia synthesis, some sort of a reactor that's beyond Haber-Bosch, so that we don't suffer the high temperatures and pressures that are necessary for the Haber-Bosch process. And here's the cycle that the Japanese, via Chiyoda Chemical in Japan, are proposing, where they have a hydrogenation plant, this could be floating wind machines in the Aleutians in Alaska, to a tanker carrying methylcyclohexane to a storage tank in Tokyo Bay, say. They dehydrogenate it and send the toluene back around to be rehydrogenated at the renewable energy source. So Wind2Green convened a technology advisory group. Jack Swearingen is a friend of John's and a retired national lab scientist, and he's got a lot of buddies that needed something to do. So they convened this group to do a landscape assessment of the other technologies out there. They did a literature search, of course, and then they followed up with personal contacts with some of these researchers. So here's a catalog of the technologies that they turned up that appeared to have some credibility. Obviously, there are improvements that could be made in electrolysis plus Haber-Bosch, but then polymer membranes and the availability of nanotechnology, which allows us to put nanoparticles either in the catalyst itself or impregnate the polymer membrane. Other nanoparticle catalysts and nanostructure, the nano world is pretty loosely defined at this time, and we wind up with composite electrolytes in a membrane electrode assembly. Naphthalene is not particularly good for that. This is the one that's primarily used in the PEM fuel cell, for hydrogen fuel cells for cars, because it's an acid and ammonia eats it. So that's not compatible. But there is an ammonia-compatible polymer proposed by the University of Minnesota. So there are perhaps solutions available. And then you would put this together in membrane electrode assembly similar to the PEM fuel cell. Proton conducting ceramics. Here's some examples. Other proton conducting ceramics. Oxides, several different kinds. Oxygen ion conducting ceramic electrolytes. Plasma, non-thermal plasma, and microwave plasma. Some of these would be packaged in configurations that look like solid oxide fuel cells, high temperature, high pressure, electricity in and hydrogen out. We've heard about molten salt electrolyte, ionic liquid electrolyte. Gentleman, professor at the University of Wisconsin-Madison says we put diamond nanoparticles on the surface, then we can get very small catalyst particles to cling to that, and the diamond itself is a catalyst, so it's another potential method. These two are a little bit hard to pronounce. This one is from Japan. This is from ETH in Zurich. I really don't understand what these technologies are. They're in the catalog. Cyclic pressurization. If you had an ICE with a very clever and intelligent valves, could you compress the air enough, rather compress the hydrogen-nitrogen mixture enough that you would synthesize ammonia right in the cylinder, and a proprietary method based on lithium. What if we had hydrogen to feed our Haber-Bosch process from artificial photosynthesis? This is exactly what the Joint Center on Artificial Photosynthesis at Caltech is looking at. They're doing a catalyst search, sort of the needle in the haystack, random search, to try to find something by accident that is a better catalyst for the water splitting with photons reaction. Biology produces hydrogen, gasification. Here's a small company that appeared at one of the conferences I went to. They have a proprietary catalyst on titanium sheet that produces hydrogen with either light or electricity input or both. And there are probably many others out there. But they're all stuck down here somewhere in the TRL 1 to 3. Research is necessary to prove feasibility. That sounds tough, sounds like money and time, doesn't it? And here are the definitions. This is something that was invented, you're probably familiar with it, by NASA to try to filter the wheat from the chaff and things that might be useful to them. This is the definition that I proposed to my client, the Ag Venture Alliance in Mason City, when they said, let's do a study of electrolysis Haber-Bosch from wind to ammonia. I said, this is the electrolysis Haber-Bosch system as I understand it. Sorry you can't read it. It's on my presentation, which you're welcome to take off the thumb drive with you. One of the best resource papers is this catalog of technologies published in the International Journal of Hydrogen Energy, I think. This has become a major reference resource. So here are the electrolytic ammonia synthesis methods. Many different ways and many variations within that. My point is that there are many emerging technologies that are going to need a lot of time and money to finish. So these are some brief looks at what the basis of these technologies are. You're familiar with a lot of these. This is what naphthalene looks like. Non-thermal plasma, solid thermochemical, plasmon-induced ammonia synthesis. Some of these are not familiar, and they may be promising. So this is the study that I did for Ag Ventures Alliance. Part of the study was putting together a simple Excel model based on something that would look like this. Here are the wind machines, here's the ammonia synthesis. In Iowa, you don't have salt geology for inexpensive storage, but there would be some other kind of storage of the ammonia itself. Here they're storing hydrogen, which then would act as a buffer for a system like this. I was assigned the price of $650 as the plant gate price for ammonia produced from wind energy in Iowa, as if this is the benchmark retail price, good as any, that prevails in Iowa at this time, $650 a ton retail to the farmer. And as you can see, it's varied over the years. This is from Keith Stokes' group, Finds. It's a very nice publication. You can see the prices varied. Here's 2012, here's 2013, and 14. Here we are today, 2014, $550 a ton. Those of you who know the ammonia market in Iowa might know better, but it is possible to track these prices. That's at the terminal in New Orleans. Then, here in the Corn Belt, you add $142 to that average for the cost of getting it to Iowa, transmitting up the Mississippi on barges or in pipelines, and then selling it at retail. So that's where we get close to the 650. I analyzed two cases based upon this simple Excel model I put together. We handled the capital expenditure, which can be very complicated depending on the ownership of your capital assets, by simply saying capital recovery factor. Tell us what capital recovery factor we should assume, somewhere between 8 and 18%. And that includes the cost of capital, whether it's debt or equity. It includes overhead and other O&M costs. It's a very simple way of trying to establish whether something is reasonable or not. So this would be the total annual cost. Case A is if your enterprise owned the wind plant. So you are making your own electricity and then converting it to hydrogen and ammonia from your wind plant. Case B was, let's assume we can buy all the wind energy we want at 5 cents a kilowatt hour, or solar, whatever renewable source energy. So you can see most of the cost is in capital recovery. There's no fuel cost because they're not buying much energy. And depending on your capital recovery factor assumption, you're somewhere between $650 and $1,400 a ton. This is the cost per metric ton at the plant gate. So you're barely competitive, maybe down here, if you can assume a low capital recovery factor for your enterprise. What if there is no grid connection? If we're going to supply all of our energy to our ammonia plant and not sell any to the grid, we can save a lot of money by not putting the infrastructure in the ground and the substation and the transmission line. So the costs go down if we don't have to put in electricity infrastructure. So when you have a universal Excel model, you can do a lot of what-if cases, an infinite number of them, of course. What if we self-generated? This is self-generation, case A2, no grid connection. So now your cost of ammonia at the plant gate is below $600. So maybe this is beginning to look competitive. But all the other assumptions in there are mine. They're not based on the market survey because there's very little information available. What if we have a high wind resource with a very high annual energy production from the wind? Now the costs go down. And the selling price, now we're down below, slightly above $500 a ton if we have a high, rich wind resource. Case B, what if we buy all of our wind energy at 5 cents a kilowatt hour? We don't own a wind plant. We're just buying it from those who have it. So now most of our cost is in the cost of buying the wind energy. Here's our capital cost down here. We have to buy some electricity now just to keep the lights on and keep the control systems running because we're not making our own electricity. We're going to have to buy that from the local utility. We can't buy it from our wind supplier because sometimes the wind is not blowing. So that's one of the assumptions we made. And this is O&M cost up here. So now our cost, if we're buying wind, for the ammonia delivered is somewhere between $600 and $700 a ton at the plant gate. Now this is green ammonia. If there's ever a carbon tax in the future, or if some customer is willing to pay a premium, like Google, to run a server farm so that they look green for our green ammonia, then maybe this is a competitive price. Here we assume that there's a higher capital cost for the EHB system than I had otherwise assumed, or higher than if the capital cost of the electrolysis Haber-Bosch system is greater. So this is our landscape assessment. This is what we've looked at today in our brief journey through the future of renewable source ammonia. It would be very good to have some ICE gensets so that we could then talk to people about complete renewable source systems, from the sources to energy services delivered, not just the kilowatt hours or liters of ammonia. The Haber-Bosch reactor at this time looks like the only good candidate for making renewable source ammonia from either hydrogen and ammonia or from renewable source electricity via electrolyzer to hydrogen, plus this should be N2. We need to deploy in Alaska a simple system, not a complex system. At megawatt input scale, our analysis should be focused because that's the increment of wind energy